Welcome back. Let's do another Thevenin equivalent, and this time we're going to use node voltage method to find V sub Thevenin. Okay, so we want to find the Thevenin equivalent circuit, and there's two steps. Step 1, we find V sub Thevenin, and step 2, we find R sub Thevenin. So unless you're using source transforms all the way through, then there's going to be these two steps. Okay, once again, we have a methodology called source transforms. We could just use that all the way through and get to the Thevenin equivalent. And that works. But this is another process where you first find V sub Thevenin and then you find R sub Thevenin. And to find V sub Thevenin, we're going to use node voltage. All right, and then to find R sub Thevenin, we're going to use open I's, short V's, open I's, short V's, and then resistor simplification. That's the methodology that we're going to use. Given a big old circuit, and here it is. It's a pretty big circuit. It's not too big, but it's kind of big. A lot of interesting stuff going on here. Okay, here's our terminals of interest A, B. We want to turn all of this junk into a Thevenin equivalent with the same A, B terminals. We've got a current source here, which is 3 milliamps. We have a voltage source here, which is 30 volts. We have a 10 milliamp current source hanging out over here, and then we have a 10 kilo ohm resistor here, and a 15 kilo ohm resistor here, and a 5 kilo ohm resistor here. So the resistor's in kilo, the currents are in milli, which is typical, and then the milli would cancel the kilo, and you end up with just straight volts. So things look okay, just kind of a run through the units and seeing if they have reasonable values, and they do. Let's see. I mean, it's good to keep a track of the reality of the situation by looking at the quantities and seeing if they're reasonable, and they are. 30 volts is a reasonable quantity, and milliamps is typical in a small circuit anyway, like your phone or something. Okay, so there's two steps. First step, we find V-Thevenin, then we kind of start over on the original circuit and do step 2 to find R-Thevenin. So I'm going to leave this original circuit just to be totally clear that we're working kind of two separate problems. I want this guy to stay here, and I'm going to redraw this stuff, and most of it's going to be the same. It seems like a lot of extra work, and it kind of is, but it's good. All right. It's a good workout, repetition, draw the same thing over again. Basically, I want to set it up to use node voltage method. And I don't want to scribble on this first diagram because I want to reuse this original circuit to do the second method. Right? So you don't want to make things too messy. You're just going to confuse yourself. It seems like you're making it a shorter problem, but you might not be. All right, now we're going to throw the nodes on there. So this down here at the bottom is 0 volts because we're using node voltage method to find V sub Thevenin, which is really just the voltage across these terminals. In the end, that's what V-Thevenin is, right? So if that's the case, then we could label the nodes on the top, keeping in mind that if it's 0 volts on the bottom, right? This is all along the bottom is 0 volts, and going up to here we're rising V-Thevenin volts. So that makes this node here V-Thevenin. If we're using node voltage method, instead of using V1, instead of calling this V1, we could just call it V-Thevenin. All right, and this is the same node right here. You could think of this as one big node right in here. So that's also V-Thevenin. Now this is another node here because we're coming across a device. So I got to label that something. I could call it V something, but I happen to know what it is because it's 0 volts along the bottom and I'm rising 30. So this is just 30 volts right here. Let's just call that node 30 volts. Okay, so now we can write an equation for the V-Thevenin and see what happens. So we'll write a node voltage equation for V-Thevenin. So node voltage for V-Thevenin. So node voltage. Remember what is the method for node voltage? We're summing the currents, at a node. And so the terms are going to be they're going to be I terms, and they're going to be V over R terms. The current terms that we sum are going to be, sometimes they'll be direct I terms, sometimes they'll be, by Ohm's law, V over R terms. So let's write a node voltage for V-Thevenin node just to see what happens. Maybe that'll be a good thing. Maybe it'll turn out well. There's two nodes here. We got this node at the top. There's no variables in that. And we've got this V-Thevenin node, which has the variable of interest. So let's just write that and see what happens. Okay, so I'm summing currents coming in and out of V-Thevenin node. So I've got a current here, which is just given as 3 milliamps. Got that guy. I've got a current here, which by Ohm's law is going to be V-Thevenin over 5. So that's coming out, and this is coming out of V-Thevenin, and then I got this voltage, or rather this current coming in, and this current here is going to be the potential difference across these two nodes divided by this resistance. So those are all the terms. So in we'll use negative, and out we'll use positive. Okay, this is kind of the method I scribbled over here, just notes to help you remember the method. Anyway, let's start summing these three currents here. So in, I've got this guy coming in, so that's negative, and it's this current coming in, and it's given by the potential difference over the current. So it's the potential difference over the resistance. So it's 30 minus V sub Thevenin over 15,000. That's this current coming into this node. Then coming out, I have 3 times 10 to the minus 3 milli. And then also coming out, I have V-Thevenin over 5,000. Okay, got this current coming in here, this current coming out, this current coming out. There's the in current, there's the out, there's the out. All right, that's the equation. There's only one unknown in there, so V-Thevenin, so we ought to be able to find V-Thevenin directly. And let's go ahead and do a little bit of math on this. So break apart this fraction right here, and you get V sub Thevenin over 15,000 minus 30 over 15,000 plus, let's move this guy close, V-Thevenin over 5,000 plus 3 times 10 to the minus 3 equals 0. So we can factor out V-Thevenin. Now V-Thevenin times 1 over 15,000 plus 1 over 5,000 equals 30 over 15,000. Moving this to the other side, minus 3 times 10 to the minus 3. So basically V-Thevenin is the stuff that's 30 over 15,000 minus 3 times 10 to the minus 3, all divided by 1 over 15,000 plus 1 over 5,000. Ugly, but it ends up being, punch this in your calculator, you end up getting a negative number, because this guy turns out to be bigger than that, so you end up with negative 3.75 volts. That's V-Thevenin. So it's negative. It's good to maybe take a little time and think about what that means now. So we typically think of the Thevenin equivalent as having this polarity on the voltage source, and then a resistance, and then there's AB. We tend to think of it that way. So there's R sub Thevenin, and then there's this V sub Thevenin, which we just solved for. So you could label that minus 3.75 volts. There's that, and so you know, so it has this polarity here, but it has a negative value, which is a little confusing. So if you want, you can also think of it this way. You could just flip the signs on that. And call this 3.75 volts, same R-Thevenin. With respect to V-Thevenin having this polarity right here, which is just the standard way of labeling the polarity on V-Thevenin. Okay, so there's that. All right, that was step one. It was a big step, but that was process one, let's call it. We found V-Thevenin. Now, generally speaking, when you do these two processes, process one and process two, you could use different methodology for each one of these processes. Here, it turns out that node voltage worked for V-Thevenin. There's other processes, other methods that you could use to find V-Thevenin. All right, but here we use node voltage. Okay, but anyway, that was step one. Now let's do step two. Okay, so step two, we're going to find R-Thevenin, and here we're going to use this method. We're going to use open I's, short the V's, and then resistor simplifications. Okay, so here, let's line it up like this. Let's take the original circuit and open the I's, that is open the current sources, and then short the V's. That's why I took the time to redraw this, right? Because we're doing step one, which we did. Then we're doing step two now. So we started sort of starting over, okay? Oh. And then we'll do resistor simplification. All right, this is the methodology that we're going to use to find R-Thevenin. So we're going to open the I's. I'll try and line it up. So there's an I right here, and I'll open that. Okay, then there's this resistor in here. This is the 10K. Then I'm going to short this V. So here I'll draw a dotted line here showing where the I was. Now there's a dotted line showing where the V is, the 30 volt guy, but it's shorted now. And then here's the 15K. And then I'm going to open this guy. And here's our 5K. And then here's AB. Okay, so line it up like this. So the 5K, bring it down. This guy, you open it. That is, take it out. And then this guy, the 15K, you just bring it down. And this guy, you short him. Bring this resistor down. And this guy, open him. So now what do we have? Well, we've got a resistor in parallel with a short circuit. Okay, so the nature of circuits, that is, what happens when you short out a resistor? The electricity is not going to go through this resistor when it has a wire right here, right? Electricity takes the path of least resistance, which in this case is a wire. So basically this kind of goes away because we've shorted it. Okay, that's another thing that happens in circuits, or the nature of circuits. All right, so that happens. So at this point we just have, oops, I left off the 5. At this point we just have a 5 in parallel with a 15, right? From the point of view of AB, you know, if you're looking down AB, you come in here, it splits to 15 and 5, and then they join back up. So it's a 5 in parallel with a 15, which works out to 3.75 ohms, coincidentally. Same number, but it's ohms now. So we're done. So well, we're not done. We're so close to being done. So then there's the Thevenin equivalent, which is what we're trying to find, is this guy. And I'm going to go ahead and flip the sign and use the positive 3.75 volts from before, just because I don't like negative quantities of voltage and stuff. And then this guy, which is a 3.75. This turns out to be kilo ohms. Oops, kilo ohms. Because it's 15 kilo and 5 kilo. You have 3.5 kilo. That's it. All right. That's pretty much what this question is asking, but you could find the Norton equivalent pretty easy just for extra, extra bonus fun, The Norton equivalent, you're just gonna move the resistors, so the 3.75 comes down here. Terminals A, B are still there. And the reason I'm doing this is because you line the polarity up here, so the current will go down that way. If I have this polarity, then this will go down, the arrow at the positive terminal, basically, the arrow head at the positive terminal. And then there's something called Ohm's law, which is I is V over R. If you haven't heard of that before. Funny. 3.75 over 3.75 K is going to be 1 milli. So that's what this is, 1 milliamp. All right, so this circuit will behave as the same as this complicated circuit up here, and this circuit down here will also behave as this complicated circuit over here. One more review of the process stuff, just because I love to repeat over and over the main ideas. We're trying to find the Thevenin equivalent. You break that up into two big processes. One, you find the V-Thevenin. Now there's a variety of methods you could use to solve for V-Thevenin. And in this particular problem, node voltage is working. So you do that and you find the V-Thevenin. Then you start over with the original circuit and you find R-Thevenin. And the methodology we're using for that is open eyes, short V's, and resistor simplification, which works when you have just the dependent circles. All right? And then some weird stuff happened where we shorted out a voltage source, which will make the resistor in parallel go away because electricity takes the path of least resistance. So there's that kind of stuff. So fun, good times. All right. See you next time.